All right. Thank you so much for giving me the opportunity to share my recent research with you all. It is on remarks on a conjecture of Huneke and Wiegand. So in the talk first, I will talk about a few important definitions that are relevant to the talk. And next, I will go straight to the conjecture of Huneke and Wiegand, which is abbreviated as HWC. And we'll mention the motivations of the conjecture, a brief history of the conjecture, and finally, I will introduce three new results of the conjecture. First, I will talk about the conjecture over two periodic modules. This is a joint work with my advisor, Olga Chek-Bash, Hiroki Matsi, and Arash Sadeghi. And this paper will appear in the Journal of Mathematical Society of Japan. And then I will also introduce my independent work for the conjecture over four periodic modules. And I will provide a proof for the four periodic modules case. Can you hear me well?
Very well.
Yeah.
Okay. So setup throughout the whole talk R always denote a commutative Noetherian local ring with the unique maximal ideal M and the residue field K. And furthermore, all R modules are assumed to be finally generated. The first definition I want to include here is the definition of tensor products. So tensor products of two modules is also a module which translate every bilinear map here to a linear map or a module map. Which means whenever we have a bilinear map from a cross product M cross N to a module P, there always exists uniquely a module map L from the tensor product to P. It turns out that the tensor product of M and N always exists, and this is unique up to isomorphism because the tensor product is the quotient module of the free module of the cross product. Furthermore, we know that the tensor product is generated by the elementary tensors of the form m little m tensor little n. So in general, an element in the tensor product would be, we have a coefficient and then the elementary tensor multiplied by the elementary tensor. Finally, if M and N are non-zero modules, then the tensor product of M and N is also non-zero. I want to note that this statement only works when R is local and M and N are finally generated modules. For example, if we look at the module Z mod 2Z, we tensor over Z with Z mod 3Z. We're gonna get zero, even though neither of the module is zero. This tensor product is zero because every element in Z mod 3Z can be represented as by an even element, which is going to be zero in Z mod 2Z. That's why the tensor product is zero. And the thing that why this can be zero is because the ring Z is not a local ring. It has many maximal ideals. That's why, because when Z is not local, then when you tensor to non-zero module, it can be zero. Next, I want to introduce the torsion submodule. So for a module M, the torsion submodule is going to be the collection of elements in M such that Rx equal to 0 for some non-zero divisor R in R. When we say a non-zero divisor R in R, we mean that the map from R to R defined by multiplied by the little r is going to be an injective map. So Rx equals 0 here, we can also look at it as X is going to be the kernel of the map from M to M defined by multiplied by R also. Another way to look at the definition of torsion submodule is that it is the kernel of the map defined by multiplied by R. The domain is M, and the codomain is M tensor K, when K is the total quotient ring of R. First, then if the torsion submodule of M is equal to 0, then we say that M is torsion free. So you can see that the torsion submodule of M is 0 means that the kernel of this map right here is going to be 0. In other words, we know that this map right here is going to be also an injective map. If the torsion submodule of M is non-zero, then we would say M has non-zero torsion. And finally, if the torsion submodule of M is equal to the whole module M, then we say M is a torsion module. An example of torsion-free modules or free modules or ideals of R. It is quite clear because if we are given this relation that the multiply by R is injective over R, then torsion-free would be this implication. So that if M equals R or M equals any power, any copies of R or any submodules of R, then the injection would hold. Therefore, free modules and ideals are going to be torsion-free. If, in particular, if we consider the integer, the ring of integer, then the torsion submodule of 2z is going to be 0, which means 2z is a torsion-free module. And because this is an ideal, 2z is an ideal, so based on number 1, we would know that it is a torsion-free module. If we're looking at the module z mod 2z, then it is a torsion module because every element in z mod 2z can be annihilated by a number 2. So this number 2 is going to be our R. Every element in z mod 2z can be annihilated by an element, a non-zero divisor in z. That's why the whole module is a torsion module. Finally, if we direct sum the previous two modules that we just consider, one is torsion-free, one is torsion, it turns out that the torsion submodule of M is neither 0 nor M. In particular, we have that the element 0, 1 is in the torsion submodule of M. This is because 2 times 0, 1 bar is gonna be 2 times 0 is 0, 2 times 1 bar is 2 bar, which is 0 bar in Z mod 2Z. So we have an element R that multiply with the element X and we get 0. That's why this X, which is 0, 1, is gonna be in the torsion submodule. Furthermore, we know that the element 2, 1 bar is not gonna be in the torsion submodule. Because for all R non-zero, we always have that 2R and R bar is not going to be the 0 element. That's why it cannot be annihilated by any element in Z. So it's not going to belong to the torsion submodule. Now we can talk about the conjecture of Huneke and Wiegand, which is abbreviated by HWC. The story starts with a very interesting properties of tensor product, that tensor products of modules usually have non-zero torsion, even when the module that we consider are very nice. For example, if we consider ring R, which is a formal power series over the complex numbers with two variables X and Y, so this is a regular ring. And we consider module M, which is a maximal ideal. So both of them are very nice. The ring is regular and the module is the maximal ideal. So both of them are nice. Then we, of course, because M is an ideal, it is torsion-free. However, the tensor product of M and M has torsion. In particular, it has this element, is the torsion element. Because this element can be annihilated by the element XY. To see why it is annihilated, it is pretty quick and simple. Xi multiplied by this, so we distribute it. We put Y where we don't have Y, and then we put X where we don't have X. Similarly, we put Y here and we put X here. So that in the end, we would have XY tensor XY minus XY tensor XY, and then it gives us 0. That's why even when we pick very nice ring, like regular rings and very nice module, the tensor product of them still might have torsion. It raises the question then, when is the tensor product torsion-free? In 1961, Maurice Auslander, in his very famous paper Modules over unramified regular rings, he found that if R is a domain and it is integrally closed, M is a torsion-free module, and the tensor product between M and the dual of M is reflexive, then the module M is free. Here, when the dual of M is the algebraic dual, which is the collection of all homomorphism from M to R. And when I say reflexive modules, I mean a module is isomorphic to the bidual itself. I want to know that free module are reflexive module, and reflexive modules are torsion-free module. So reflexive stay right in the middle of free and torsion-free modules. Then 3 decades later, Huneke and Wiegand improved the result of R slender. In particular, they proved that if R is a Cohen-Macaulay domain such that R localized at P is a hypersurface for all prime ideals P, such that the dimension of RP is at most 1. M is a torsion-free module, and the tensor product of M and the dual of M is reflexive, then we can conclude that M is free. I say that the Huneke-Wiegand theorem is the improvement of the R-slender theorem because if R is an integrally closed domain, it is a normal domain, which means RP is a regular ring if the dimension of RP is at most 1. So from being regular, from the assumption of being regular to the assumption of being hypersurface, that's why it is an improvement. So this is Huneke, and this is Dr. Wiegand, who is also my academic grandfather. This picture was taken last year when he was making a talk in the Huneke-Wiegand conjecture also. Then in the same paper, Huneke and Wiegand themselves also conjecture that maybe we can remove all of the localized assumption on the ring, and this is enough to assume that the dimension of the ring is positive. I want to make a note that you can see both of the previous theorem that were proven, they only looking at like the assumption on the rings were reduced to the at most one-dimensional case. And it turns out that the conjecture of Huneke and Wiegand also works that way, that it can be also reduced to the one-dimensional case, so that you can see from here, the dimension is positive to here. It's enough to look at the dimension is 1. Furthermore, because one-dimensional domains are Cohen-Macaulay domains, so we don't even need to say that the R is a Cohen-Macaulay ring. Moreover, because of the beautiful properties of the one-dimensional rings, so the assumption C here, assumption of the tensor product, it suffices to assume that the tensor product is torsion-free, while in the original conjecture, we have to assume that it is reflexive. I also give an example to show that the torsion-free assumption on the tensor product is only sufficient over one-dimensional ring. Here, this ring is a two-dimensional ring, also hypersurface domain. So this is not true, this is true, and I is an ideal of R. So of course, I is going to be torsion-free. Now we need to, torsion-free, so it should be a check mark. Then we need to check condition C. We can prove that the dual of I is isomorphic to R. That's why I tensor, the dual of I, is going to be isomorphic to I, which is also torsion-free, so it works also. However, this ideal I is not a free module because it's not principal. So this is not a torsion-free module. Therefore, if the dimension of the ring is at least 2, we need to assume that the tensor product is reflexive. Torsion-free is not enough. The next motivation is a reformulation of the Huneke-Wiegand conjecture over Gorenstein domains. So if R is a Gorenstein domain, then assumption B is equivalent to saying that M is a maximal Cohen-Macaulay module, which means the depth of M is at least the dimension of R. Furthermore, the assumption C is also equivalent to saying that X1 of the pair MM is 0. Then these two equivalent that is colored B and C are actually remind us of a very famous conjecture, which is the Auslander-Rayton conjecture. It said that if R is a Gorenstein ring and M is a maximal Macaulay module, such that Xi of the pair MM vanishes for all positive I, then M is free. So then you can see that the Huneke-Wiegand conjecture is an improvement of the Auslander, not improvement, is a general, it is a special case of the Auslander-Rayton conjecture, because here it only requires one X to vanish, but here it requires for all X to vanish. That's why it is a special case of the Auslander-Rayton conjecture. I also need to emphasize that the Auslander-Rayton conjecture was originally given over art in algebra. I give it in this version because this is easier to read and it's more convenient for everyone. This is the version over Gorenstein ring. Finally, I will introduce the version of the Huneke-Wiegand conjecture that I study, which is a little bit more general than the original version. So instead of looking at the domain, I will look at the local ring when the module M has rank. Here, when I say a module has rank, if it is locally free of the same rank for all associated prime ideals P of R. Note that if R is a domain, then M would have rank. That's why the version that I study is a little bit more general than the original version. In the rest of the talk, whenever I say HWC, I refer to this version. We study over local ring when the module has rank. I also give one example here to indicate why the rank assumption on the module or the domain assumption on the ring is necessary. I give an example of this ring R, which is not a domain, but it is one-dimensional hypersurface ring. This module M is torsion-free also. Now we still need to check condition C. So M star here is actually isomorphic to M, so that when we tensor them, it is the same as R mod X, tensor R mod X. And recall that in general, R mod I tensor R mod J is isomorphic to R mod I plus J. So that this here, when you add the ideal X and the ideal X, you still get the ideal X. So that this is the same as M. So the tensor condition C here also works. However, this module M is not free. Therefore, without the domain assumption, the conjecture will fail. Similarly, here, it's still a one-dimensional ring. M is torsion-free. However, M does not have rank. The tensor product is also torsion-free, but the module is not free. Again, we need the rank assumption on the module. Now, let's move to a brief history of the conjecture. First, I will mention the results over complete intersection rings. Here, whenever I say a ring R is a complete intersection ring, for convenience, it will be isomorphic to the quotient ring S over the ideal generated by sequence F, where S is a regular ring and the sequence F is going to be inside the maximal ideal square. And it has to be a S regular sequence also. I want to assume that F is inside N-square because with this construction, the codimension of R is going to be the same at the length of the sequence F. So the first result I want to record here is that the conjecture holds over regular rings, which means complete intersection rings with codimension 0. So over regular ring, then M always have finite projective dimension. And from assumption A and assumption B, we know that depth of M is the depth of R. So from these two results, then we know the projective dimension of M is going to be 0 as a result of the Auslander-Buchholz formula. All right, next we're going to look at hypersurface ring. Is when the codimension of the ring is 1. So Huneke and Wiegand proved that if R is a hypersurface rings and M and N are all modules such that the tensor product of M and N is torsion-free, then either M or N is free. Here we aim to prove the conjecture, the Huneke-Wiegand conjecture. So we're not going to look at any N, but we're going to, in particular, we're going to look at M star. So we can apply assumption C here. So that if M tensor M star is torsion-free, then either M or M star is free. Then I'm going to use a result of Ogachev-Bash, Shirogoto, Ryo Takashi, and Naoki Taniguchi, which is published in 2019. They proved that if the depth of R is at most 1, which is going to be satisfied by assumption A, and M is a torsion-free module, which is going to be satisfied by assumption B, then M is free if and only if M star is free. So using this result, we know that either M or M star is free, we imply that M is free, which means the Huneke-Wiegand conjecture holds over hypersurface ring. So, in conclusion, the Huneke-Wiegand conjecture holds for complete intersection rings R with codimension either 0 or 1. However, the conjecture now is still open in the general sense if the codimension is at least 2, even when the codimension is 2 and M is an ideal. However, there are many specific cases that were proven, but in the rings general sense, then it's still open. The next result is a motivational result of our paper. That's why I include here, which was published in 2020 from my advisor Ogachev-Bash, that he proved that the Huneke-Wiegand conjecture holds if M has finite complete intersection dimension and M has bounded Betti numbers. I want to note that this is a generalization of the previous result that I just mentioned, because if R is a complete intersection ring with codimension either 0 or 1, then these two assumptions would hold. That's why this gonna cover the previous result that I just talked about. I want to make a remark that we may assume that the module M in the Huneke-Wiegand conjecture has no free direct summand, because we can see, for example, if M is F, direct sum X, and F is a free module, and X has no free direct summand, then we're gonna apply the conjecture for X. And if it works, then we can conclude that X is free, then we direct sum with F, then we can also conclude M is free. So this is okay if we may assume that the module M in the conjecture has no free direct summand. And with that extra assumption, then the two assumptions in this theorem implies that M is isomorphic to the second CAAG of M, which means a minimal free resolution of M has period 2, or it repeats after every 2 steps. So now the motivation, the goal is to actually study the Huneke-Wiegand conjecture over modules of this form so that we can provide a more general result for this conjecture. In the paper, which is a joint work with my advisor, with Hiroki Matsi and with Aras Sadeki, we proved that if R is a domain and M is 2 periodic, then the conjecture Huneke and Wiegand would hold. In fact, we prove a more general result that the Huneke-Wiegand conjecture would hold if M is any periodic module and the pair M comma N is torrigid for all R module N, which means, in other words, M is a torrigid module. Here, we say Mn is torrigid if the tor of the pair Mn vanishes somewhere, say vanishes at N, then it would vanishing from everywhere after N. Then I actually improved the previous result. I removed the domain assumption in the result. In fact, I also proved that the conjecture Huneke and Wiegand would hold if M is any N periodic module and the pair M and the push forward of the dual of M is torrigid. This number 1 here stands for the push forward of M. If we have time at the end of the talk, I will define the push forward and some properties of it. If not, then I will skip it. But this little one at subscript 1 right here, it stands for the push forward of the module. So here, you can see that instead of for the previous result here, instead of I have to check the torrigidity of the pair Mn for all module N. Now I prove that it is enough to look at one pair, M comma push forward of M star. So here, because of that, when N equals 2 here, then we need R to be a domain for this statement to hold. However, because I only need to check over one pair like this, then I don't need R to be a domain. In particular, it was proven that if R is a one-dimensional ring, okay, sorry, technical issues. All right. It was proven that if R is a one-dimensional ring and M is an R module with rank, such that M is the second, is a 2 periodic module, then this thing does not just hold for one pair M and the push forward of M star. It's actually hold for all of the pair of this form. For any X with rank, it would hold. In particular, for the Huneke-Wiegand conjecture, we only need to look at X equals N. I will use this proposition later in the proof. That's why I want to stress. If M is a 2 periodic module and it has rank, then this pair is always torrigid for all module X right here. So now finally, the result that I want to give a proof in this talk is the last result, number 3. If the Huneke-Wiegand conjecture holds if R is a Gorenstein ring and M is a 4 periodic module. In particular, I include the theorem here, the whole statement. Let R be a Gorenstein ring and assume that the dimension of R is 1. M has rank, the tensor product of M and the dual of M is torsion-free, and M is a 4 periodic module, then M is free. Now we will proceed to prove that theorem. Before proving it, I will provide the definition of the R-slender transpose, which play a crucial role in the proof. So if we have a part of a minimal free resolution of M, then we would dualize it, and the transpose of M here is going to be defined as a co-kernel of the dual of the map partial one. So it is clear that the first CAAG of the transpose of M is going to be here, and the second CAAG will be there. That's why the dual of M is going to be isomorphic to the second CAAG of the transpose of M up to free sum N. After introducing the definition of transpose, I'm going to include here 2 facts about the transpose and the push forward. And again, if I have time at the end, I will provide the proof for these 2 relations. First one is that tor 1 of the pair M comma the push forward dual of M is going to be injective to the tensor product of M and M star. For number 2, tor I of the pair M and the push forward of M star is isomorphic to tor of I plus 1 of M and transpose of M. In fact, this thing can work for any pair of Mn. It doesn't have to be M and N. But here I only need it to be the same module M. The third tool I want to mention here is the relation that provided by Goto and Takashi in 2017, that the tensor product of M and dual of M is torsion-free if and only if x1 of the pair M is 0. And lastly, from the from the four-term exact sequence of R slender and Bridger, when R is a one-dimensional Gorenstein ring and M is a maximal Cohen-Macaulay module, from this exact sequence, we will include the tool number 4, which means x1 of the transpose of the CAAG of M with x is isomorphic to tor k of the pair mx for any positive k. This is because xk of mr will be 0 because M is a maximal Cohen-Macaulay module over a Gorenstein ring. So now let's prove it. First, I want to prove a claim that tor 1 of the pair M on the push forward dual of M is gonna be 0. From assumption from the tool number 1 with assumption C, then we would know that tor 1 of the pair M and M star push forward will be torsion-free. Because tor 1 of pair M and the push forward of M star is a submodule of a torsion-free module. That's why it's also torsion-free. Furthermore, B with M has rank will imply that this tor module is torsion. So then, altogether, a module is both torsion and torsion-free, then it has to be 0. Because let's say if X is a torsion-free module, we know that the torsion submodule is 0. But if it's a torsion module, then the torsion submodule is gonna equal to the whole module. So if a module is torsion-free in torsion, then it has to be 0. That's why we prove the first equality. Next, we're gonna prove the second equality, which means tor 3 of the pair M and the push forward of the dual of M is gonna be 0. This is a little bit longer. From tool number 3 and assumption C, we know that 0 is gonna be equal to x1 of the pair MM. And there is an isomorphism that this is going to be isomorphic to x1 of the pair M star and M star. This is due to Huneke and Jorgensen. And the isomorphism only takes place when M is a totally reflexive module, which holds in this case. And then earlier, we just showed that the dual of M is the same as the second CCG of the transpose of M. So I'm gonna rewrite it in this way. Now, because R is a Gorenstein ring, so then we can do dimension shifting to get x1 R of the transpose of M, comma transpose of M is gonna be isomorphic to the above one because we're gonna add 2 for the first component and, oh no, it disappeared. All right, why did it disappear? But this is gonna add 2 and this is gonna be subtract 2 from the above dimension shifting. And from here, we can also keep rewriting because from assumption D, we know that M is a 4 periodic module. So instead of writing M for the first component, I'm going to write the fourth CAG of M. Like this. Then we can use number 4 to find the isomorphism with TOR R4 and M, comma, transpose of M. This K is equal to 4, and X is going to be transpose of M. So that finally, we can also use the isomorphism happens at number 2 to get TOR 3 R of the pair M, comma, the dual of M, 1 to be 0. This is when I equals 3. And that is what we want because we have a 0 back here. That after a bunch of isomorphism, we prove that TOR 3 of the pair M, comma, the push forward of the dual of M is equal to 0. So the second equality here also holds. All right, finally, we will proceed to prove that M is free, having the claim that we just proved. Now I'm going to set X to be M direct sum with the second CDG of M. With this, we know that X is going to be 2 periodic. Because M is 4 periodic, then we take the second CG of X, we're going to see the CG would be 2 and 4, which would be the same as 2 and 0. That's why it's isomorphic to the second CG of X. Furthermore, assumption B says that M has rank, so that it would imply that X also has rank. So in the earlier previous proposition, we said that I included that if any 2 periodic module has rank over a one-dimensional ring, then it is TOR rigid with all of the module of this form, which is the module of the form, the push forward of the dual of the module. This is based on previous proposition. Furthermore, with the construction of X, we know that from TOR 1 and TOR 3 of the pair is 0. We know that TOR R1 of the pair X and the push forward dual of X is also 0. So from these two facts, that it would imply that TOR I of the pair X and M star 1 is 0 for all I positive because it is 0 starting at 1. So now it's going to be 0 everywhere. And because X is just the direct sum of M and the CG of M, then we can also conclude that instead of X and the push forward of M star, we can conclude M and the push forward of M star for all I positive. In particular, we know that 0 is the TOR 4 of this pair. So that it is isomorphic to TOR 5 of the pair M and transpose of M. This is due to the isomorphism number 2 at I equals 4. And because M is 4 periodic, this is going to be the same as saying TOR 1 of the pair M and transpose of M. Hence, whenever TOR 1 of the pair M and transpose of M is equal to 0, then we can conclude that M is free. This is due to Yoshino, the result of Yoshino. And we've finished with the proof of that theorem. Now, because we still have a little bit of time, I will introduce the push forward to you. So if X is any R module, then I'm gonna consider the dual of X, and I look at the minimal generating set F1 to Fn of the dual of X. I look at the free cover of dual of X, which is the map that we make to construct the minimal free resolution that send every generator to a generator. And then I'm gonna compose that map, compose a bunch of maps to get the map alpha X. So first I'm gonna look at the delta X map, which is a natural map from X to the bidual of X. Then I will compose it with the dual of pi. And finally, because the dual of a free module is also a free module, I will translate it to this, put it with this isomorphism. Make a long story short. So alpha X define every X to the element F1 of X, F2 of X, all the way to Fn of X in R to the n. And the universal push forward of X is defined to be the co-kernel of this map, alpha X. The first remark that I include here is that the kernel of alpha X is the same as the kernel of delta X. This is pretty quick because the map pi is surjective. So when we dualize it, it's gonna, the dual pi is gonna be injective, and the isomorphism here is also injective. So the kernel of alpha X is decided by the kernel of delta X. In particular, if X is a dual module, so if it's torsionless or the kernel of delta X is 0, then we obtain a short exact sequence of the form 0 to m star to R to the n to the push forward of m star. Then when we tensor with any module Y, then we're gonna have this is the number 1 in the tool that I did earlier, that the inclusion of tool 1 of the pair Y and the push forward of m star to the tensor product of Y and m star. And this is the number 2, that when we look at the long exact sequence from tensor product, we would know that the index of tour of Y and the push forward of m star is going to be 1 more than Y and m star, which is isomorphic to tour of I plus 1 of Y and transpose of m, because m star is isomorphic to the second CCG of transpose of m. So we're going to add 2 more into the index to obtain the last isomorphism. And here are a few references that I used in the talk. I have the very famous paper of Auslander, or also the conjecture of Auslander-Wrighton, and the Huneke-Wiegand paper that stated the Huneke-Wiegand conjecture. I also include the paper of Oger-Chelpash that had the motivational result for our paper. Then this is the paper that we did in the 2 periodic case over 2 periodic modules over domain. This is called Remarks on the Conjecture of Huneke and Wiegand and the Vanishing of Cohomology, and it's published online and to appear in the Journal of Mathematical Society of Japan. And finally, my further work is gonna be in progress. And that's it. Thank you very much for listening.